already know. For example, this section 4, section 5, section 6, these are, you have learned these in other contexts. So we'll go through them very quickly. These concepts are already known to you. And so this is the first part. We will selectively read parts from this, portions from this part of the book. The second part of the book talks about certain very common variables and certain very common techniques of measurements. So this is, you can learn. This is a bit. It creates a little confusion. We'll have to deal with it. That you can either learn it from the point of view of techniques of measurement. So if you learn about resistive sensing elements, there could be so many elements. So something measuring strain can also have resistive sensing. Something measuring temperature can also have resistive sensing. So we will see. Basically, without going into it right now, let me just say that this is some typical types of instruments. We'll learn some things about them, how they work, what is the basic physics behind, and how. We are electrical engineers, so we will also be interested in knowing that how the signals from the basic sensor are to be conditioned so that they can be used, displayed, measured, etc. So that is the second part. For some common instruments, and part C is for some special measurement systems. Particularly, these are important. For example, flow measurement is very important, especially in an industrial situation. All of chemical engineering is very much dependent on flow measurements. Most control systems are dependent on flow measurement. And some of these we will not talk about, again, because of the fact that we are not going to be instrument designers. So these heat transfer effects in measurement systems, these are some things that we'll skip. But in this, we'll basically study flow and ultrasonic. These two are very common instruments. We'll not study gas chromatography. And I was thinking that we should try to cover two things. One is a simple camera as an instrument. I think it has a lot of applications. It's not there in this book. So this camera as an instrument will be I'll try to cover. I'm not an expert on that, but we'll try to read up from some good source. The other is a concept of virtual instruments. So there are, when you can actually, when you are trying to measure things, it's not always voltages and currents and temperature which you measure. You may also like to measure, resistance, for example. So for example, when you try to understand whether a battery has become old, it is aging, how far it has aged, if you want to determine, very important for automotive batteries. Then one of the indicators of that is its internal resistance. As a battery grows older, its internal resistance increases. So if you want to find the internal resistance of a battery, you cannot, it's an internal resistance, right? it is an equivalent effect of all the things that are there inside that pouch. Various kinds of, it's all, chemical things, electrolytes and, separators and various layers on which these materials are deposited and stuff like that. It's not like a resistance that you see in the machine's lab. So how do you get that resistance? So you have to derive it in terms of voltage and current measurements, and there can be elaborate algorithms to understand that. Or if you want to measure how much charge is there in a battery, that also you cannot directly measure. So these are virtual, but you can, using primary instruments like voltage and current, you can construct algorithms which are basically computing artifacts, probably implemented in an embedded system board in the car, which in the battery management system, which will tell you how much charge is there in the battery. So in that sense, it is an instrument, but it is a virtual instrument because it's not a direct instrument. You use other measurements from other instruments and then use an algorithm to derive quantities like internal resistance of a battery or the charge in a battery. So we will study basic fundamentals about how to construct such instruments. That's my wish. I don't know how the course will progress and where we will end, but I thought that these are modern concepts which are coming up and we can take a look at that. So this is the plan. So there are 3 parts of our course and this book is also divided into 3 parts. So we'll follow that, right? So at this point, is there a question? Do you have any, did you follow what I said in general? If somebody says yes, sir, it will be helpful.
Yes, sir.
Yes. Good, thank you. So let me go back to my, so we'll start with part A now. Yeah, I have a class. Come back at 12. Yeah, what is it about? Yeah, about that. Yeah, so come back at 12. Yes. So so let me open the book and get into part A. So the first thing that we would try to understand. So I'm going through the book and this is a PDF which is freely downloadable. You can get it from the internet. At least I did not face any problem. I did not feel that I have done something improper by downloading this. So hopefully it is permissible. Another thing is that I think I've forgotten this, but it'll be good if you remind me to record. Are we recording? I think we are recording. No? Is the recording on? Yes, the recording is on. Good. That's fine. I sometimes forget. So if I forget, please remind me in a class. So we will. You can read this. It's a very nice thing. So it's a very nicely reading book. So we'll first look at this diagram. This is the first thing that we want to read. So if you have most instruments, in fact, almost all instruments are structured like this. It is important and good to understand this structure. Let me try to because then I'll be able to write it. Yes. So this is the real. Suppose you are trying to sense temperature. Okay, we'll give an example at the end. After this, so suppose you are trying to sense temperature in let's say in a furnace. We have to select pens. So let me select this. That's okay. Yes. Yes. So this is the input. Why is the black not so good?
So that is a pencil option. You have to select a marker.
Yes,
Just
that's a pencil. So I have to take it as a pen, right? Okay. So here, is it a pen? Looks like maybe. Yeah, it looks like a pen. Correct. You are right. Right. So correct. So this is the this is, let us say, the furnace. We are trying to measure the temperature in the furnace. We are in an industrial instrumentation course. So suppose this is the furnace. And there exists some temperature which is its true value. Really, there is some temperature in the furnace. Actually, the temperature in the furnace will be varying. But we are talking about the point where the sensor is. So this temperature is being sensed by the furnace. So the furnace wall is there. In the wall, there we will study this. In the wall, there is a what is called a thermo well is created, and the temperature sensor is inserted into the thermo well. So this is the furnace where you have the true temperature. So this is the sensing element. It's probably a thermocouple. We'll see what thermocouples are. So that is the sensing element. Now this sensing element, this thermocouple produces a small voltage. So it's a millivolts range voltage. So we need a signal conditioning element to bring it to, maybe you have an amplifier, or you may have an amplifier. You may also have a cold junction compensator, because thermocouples do not give absolute temperature, but the difference between the temperature difference, the voltage is cold junction compensation. So there are some specific circuits which are required, which will be fed to, these are signal conditioning elements. These are very signal specific. So these are not not signal specific, these are sensor specific. So that's why when we use the word conditioning, we mean, for example, it may be a Wheatstone's bridge, it may be a cold junction compensation circuit, it may be a what is that called? For piezoelectric, it could be a charge amplifier. So these are specialized circuits which are specifically required for a particular sensing element. That's why then we call it signal conditioning element. After that, we get a general voltage that also we may process further. So you may filter it. This is a general purpose operation. Filtering is a general purpose operation, whether it is coming from the thermocouple or the strain gauge or the piezoelectric crystal, the filter is the same. So that is the signal processing element. So when we say signal processing, we typically mean general purpose operations. When we say signal conditioning, we mean sensor specific circuitry. Then it may also involve some AD conversion, etc. And then finally, here it is written as data presentation. I would like to use the word application. It's not, although instrumentation is typically there is a presentation of data, but so it's finally the data is used in some application. This application could be a controller. It could also be a machine learning algorithms. We use a lot of data nowadays. So it goes into some application. It may be a display, maybe a simple display to an operator. So this is the general purpose architecture of a measurement system. So we will move on, and you can see that what kind of things are signal conditioning elements, what are signal processing elements, for example, ADC. It could be a digital filter, etc. And then finally, you have a data presentation element. They have given only, display kind of applications, but in today's thing, this can be further sort of broadened. That's why I use the word application rather than data presentation here. It may go beyond a presentation element. It may be used in various ways, right? This you can understand, and there are various examples given. You can see some of these examples. We'll see examples in our assignments also. But now so this is the first chapter is being concluded. So the message in the first chapter is nothing but how instrument systems are basically structured. So they are structured into these 4 blocks, which you can see. This is the simple sort of summary of. So, and there are always, you can always see that there are variable conversions happening. So temperature is getting converted to a small voltage. That small voltage is getting converted to another high voltage. In some case, let us say for a strain gauge, strain is converted to resistance. Resistance is converted to voltage. Voltage is converted to higher voltage. So it's all a series of voltage conversions, variable conversions which happen in a sensor system. And finally, it becomes a digital. Usually, in today's context, it becomes a digital data, and which is used in some application. So that's pretty simple. Now we will see. We are very interested to get the true value of that true value, but due to various reasons, we will not get a true value. As you know, there is always measurement error, always. In principle. So we would like to understand that how much is this error before we use it in an application. We would like to know that how much is this error and what is the nature of the error, so that we can interpret the data that we are getting from a measurement system. It's very important to understand that. So last week, one of my friends who is a professor here, he was trying to decide whether he should start taking blood sugar medicine. Actually, he was not taking medicine. He was trying to control it using, his diet and walking and stuff like that. But at one point, his blood sugar started increasing, and he felt that possibly it's not good not to keep it in control. So he was trying to decide. When he was trying to decide, he was trying to measure it. Being a scientific person, he was trying to measure his blood pressure every day, before food, after food, and then he was trying to make sense of the data. So it's very important to these situations we regularly encounter in life, either in industrial situations or in personal situations, that we will have measurement systems and we'll have to make sense of data. Exactly same thing sometimes happens to my blood pressure, right? So let's understand what affects the measurement of a measurement system, how it is captured. If you take a data sheet, if you read a manual, how it will be stated, how to make sense of that manual. And finally, when you get a reading, see, the problem is, it's very important to understand that, let me go to the whiteboard. This is a very important thing to understand, that you see, is it there already? It's coming. I think it's loading and it takes time, and it has pixels and other things. It's slow. Already the display is not good. Are we having is it okay? Let me see this. No, this is different. Where is my whiteboard? Yeah, it is taking time. So slow, eh? It's crazy. This is the snippet. This is the whiteboard. Very slow. Well, it's not writing. So, okay, let it come up. But what I was trying to say is that, let me say it in words, that do you realize this, that when you are, what is the instrument doing? The input to the instrument is the true variable. Whatever temperature exists in the furnace. The output of the instrument is an indicated variable, right? It gives a reading. That is its output. When you get the reading and you are trying to decide on the true variable, you are trying to invert this map, right? So you are, to your interpretation system, it is the measured variable which is the input, and your decision, you are trying to understand what is the true variable. So, this is an interesting point. The characteristics of the instrument, if you think of the instrument as a system, then when you read its data sheet, you will always see that if it is given some temperature of 200 degree centigrade, whether its output is going to be whether between 199 and 201 degree centigrade. That is what will be stated in the data sheet. But you have to use that to understand that if you get a reading of 200.2, then what is the range in which the true temperature exists? So you have to invert this map. This is very important to understand. Right? So with this understanding, let's go into, first let us see how instruments are characterized. Then we will see how to make sense of it. So is this clear to you so far? Any questions? Did you understand this inverting the map?
Yes, sir.
Is there somebody who has a doubt? Nobody has it. Very good. Okay. So we go into, so now you see, so this is the picture. We want to find out, basically we want to find out the input output characteristics of the instrument. Now before we do that, we want to, I'll go in a slightly different sequence, and I'll go to a different picture first. First of all, we have to understand that what causes the error. That is very important to understand. So I want to go there. So I want to talk first about this diagram. So you see, this is a general model of an instrument. It's a numerical model, right? So it's a little specialized. I would have drawn it in a slightly different way. So, but has the whiteboard come up? Yeah. Yes, it has come. This is a different thing, so I will have to take a new board. Create new whiteboard. Okay, so I will we will take this diagram, and so first you see, let's see this diagram, then we can see this diagram in a slightly different way. So so what is it? So first of all, you have to understand that there are Why is it that is not coming? I think it's slow. That's causing the problem. Anyway, first of all, you want to understand that the system, the sensor, when I say we are all only concerned about sensors. So there is a, let us say we have a, load cell. You know, load cells, I don't know, you have seen when you go on the highway, you see there are some way bridges, right? Way bridge. They weigh trucks. So they use load cells. The truck goes on a platform, goes and stands on a platform, and the whole weight falls on a columnar structure, and it causes a lot of strain. And there are devices called strain gauges, which whose resistance changes, and it gives its resistance changes, and then there's a circuit which causes some output. So what is the, so let us see the whole sensor as a whole. So the output is whatever is the reading, and the input is the weight of the truck. Next, but you see that this load cell is made up of strain gauges, whose resistance changes due to weight. But resistance change can also occur due to temperature change. So the resistance of the strain gauge is also depend on ambient temperature, and maybe it will create an error unless you take care of it. It will create an error between a reading of the same truck for the same weight taken in summer and winter. So you see that we want the output to be affected by only the weight, but there are other undesirable quantities which also affects the output. So this is a fundamental fact of instrumentation. Because in instrumentation, remember, why we are thinking of these things is because we want to split hair. That's our job. We want to, if you are designing, whether you are interpreting, we want to know whether it's a 2% error, 3% error, 5% error, whatever it is. So we want to split hair, and we are splitting hair, right? So first of all, we have observed that there are various, other than the desired input, the output is affected by other things, and we have classified them into two types of inputs. These are undesirable things which also affect the output, and we should understand their effects to understand what kind of errors are caused by them. So we have two types of output of these, these sort of disturbance or error creating spurious, undesired inputs, which also affect the output. One of them are called modifying inputs. So this is important. Yeah. So we have modifying inputs and we have interfering inputs. Look at the block diagram carefully. So what is the difference between them? The interfering input is, you can see here, is getting added. So the reading first, forget about this part. So this part is the part which is being affected by the modifying input. So for the time being, let us ignore it. Let us ignore this part also. We'll talk about them presently. So the desired input is coming, and we see that the interfering input is an additive effect. It is getting added as an error. So there is resistance change is happening due to load. Resistance change is also happening due to temperature change. So the total resistance change that we are seeing in the weighbridge is actually a sum of resistance change due to the weight and the resistance change due to temperature. So temperature in this case is an interfering input in this sense, because it is giving some delta R. Some delta R is happening due to the weight, which is the desired quantity. We want to see how much resistance change happens due to the weight. That's what we want to measure. So we want to sense only this delta R, but it so happens that there is another delta R which is coming due to temperature change, and that is the final thing which is coming to the output. Let's ignore, because for this weighbridge situation, the dynamics is not that important because it's a slow measurement. So this is interfering input. What happens in the, now let us rub it off, and so where is the eraser? This is the eraser, right? So we can rub it off, no? Is it rubbing? Yeah, very good. At least it's doing something. It's a bit slow. Okay. So now let us ignore this part of it. We have again selected a pencil. So now let us ignore this part of it, and this part of it, and this part of it, and only look at this part. What is the modifying input doing? So now you see that the modifying input, do you see that the modifying input output, this I, it is adding a KMIMI term into it. This is KI. So what is happening is the total is K plus KMIM into I is coming at this point. I hope you agree. So effectively what the modifying input is doing is that it is changing the gain. This is now K has become K dashed. And this, how much K will change, how much K dashed is different from K is dependent, that amount is now different. This amount is delta K is equal to K dashed minus K. Do you agree? So the effect of the modifying input is to change the gain. So it is a multiplicative effect. The error that will happen finally, it is dependent on I. It is now dependent on I. Here the gain, the error that was happening is not dependent on I. It was Ki II. So you see that the nature of the error being introduced in the two cases is somewhat different. So for example, but it may happen, So these IM and II, are these separate variables necessarily? Not true. They may be the same variable. For example, the temperature change that we just now said that it introduces a delta R due to thermal, coefficient of resistance and is seen as an interfering input. We just saw that. On the other hand, it could happen that this K dashed, this K could be a function of temperature. It could be. For example, the gauge factor, how much strain causes how much resistance change, is called the gauge factor of a strain gauge. We'll study. So the gauge factor is actually a material property which depends on temperature. So now, due to the same change in temperature, there is a thermal coefficient of resistance that is introducing an interfering effect, but it also changes the gauge factor. So when the gauge factor changes, then this K itself changes to K dashed, and that introduces another error. Now the resistance change is different, which is due to temperature. So at this point, I would come back and again ask you whether this is clear or not. The difference between the interfering input and the modifying input. Is this clear?
Sir.
Is there any question?
Yes, sir. Sir, in the modifying input, is it a variation of weight that is coming into play? Or it is something else which is coming in parallel?
No, it is not the variation of weight. It is not the variation of weight. See, a certain weight, what are we doing? We'll see this. We are sort of a little bit jumping steps, but let's jump steps. So what is happening in the weighbridge? In the weighbridge, there is a strain gauge. So you put weight. So you put weight, and you get a delta R, which is the property of the strain gauge. Then this delta R change you put in a Wheatstone's bridge. So this is strain gauge. This is Wheatstone's bridge. So this delta R changes will be converted to a delta V using a standard unbalanced Wheatstone principle, which we'll see. You already understand. So now this strain gauge. So there is so now this delta, actually there is a factor which says that delta R by R is equal to gauge factor times the strain epsilon. So this gauge factor is a material property of the strain gauge. Now this gauge factor is actually, it's a function of temperature. So when temperature changes, this gauge factor value changes. So now for the same weight which causes a certain strain, this is again, weight by area, which is strain, which is stress, divided by Young's modulus will be the strain. So the weight is the thing that you want to measure. So now you see that the proportionality constant between delta R and epsilon changes due to temperature. So the gain changes. This is a modifying input effect of temperature. There is another effect which is a thermal resistance change where R changes by R0, R equal to R0 plus alpha R0T, right? So that R change also causes a change in delta R. That is an additive effect. That is an interfering effect caused by the same temperature change. Is this clear?
Yes, sir. Okay, sir.
Sir, so here modifying input and interfering input both are temperature.
Yes, exactly. So temperature can both act as a modifying input and as an interfering input in a measurement situation. So there need not be, distinct variables all the time. Right?
Yeah, got it.
Yeah. So now let's go back to this diagram. So these two are two effects which causes error. There are other effects. So typically we will see that we like to say that instruments are linear. By linear, let's take a simple approach. That means output y is equal to some constant time input u. Yeah, I'm not saying in that linearity superposition sense, although that is, I mean that will also come. But initially, let's talk about, there are two situations of measurement. One is where the input quantity is varying. That's called a dynamic situation. That the input quantity is changing. If you want to see that measurement in that situation, then all these transfer functions, differential equations will come into play. But let us initially talk about a simple situation where we are trying to measure steady values. So when you are trying to measure steady values, at that time, when we are trying to measure steady values, at that time, this need not be considered. Only it will act like a gain. Any transfer function, when s tends to 0, you know this already, you are in final year. It'll be represented by a gain. So let's not talk about it. So we like to say all instruments, we like to say that it is a linear thing with a which has a sensitivity or a gain. Why do we say that? We say that because if we construct it like that, then it's very easy to use. You only have to remember one number k. The moment you get some reading, some voltage, you know the k, divide, you will get the input quantity, which you want. So it's very easy to use. So everything, we have to remember that we have to construct this is somebody who said this? This guy who, Steve Jobs, that you may have, no, was it Steve Jobs or was it Jeff Bezos? Anyway, a lot of people have said this. So that it has to be, technology has to be complex, but it should look very, very simple to people. So you can take a lot of pains in design, material selection, electronics to make things linear. Why? Because you can use the instrument using only one gain value. So you try to see whether this, but obviously it will be an approximation. Nothing is linear if you split hair. So the question is that for the purpose of your measurement, the application, the kind of accuracy you need, is it okay to look at it as linear? So there are lots, and almost 90, I would say, more than 90% of cases of measurements, we will probably, it'll be good enough to say that it's linear. You can call it away. There'll be a slight error. So sometimes what we try to do is we try to hide the nonlinearity into an error description when it is small enough, just to make this instrument look simple. But if the nonlinearity is very prominent, then of course you cannot consider it to be linear. Then if you consider it to be linear, you will get lot of error. That makes no sense. Then every reading, you get a reading by considering a linear model that its weight is 1 ton, and then there could be an error of plus minus 20%. Then it makes no sense. But if it is plus minus 1%, probably it makes sense. So from that point of view, instruments are sometimes considered as linear, and the non-linearity, but there is always a non-linearity. If you really is willing to take, look closely enough, there'll be some amount of deviation from the ideal linear line, and that is being described by this part in block. So actually there is a nonlinearity. You may like to call it a desired part of the instrument. You may like to call it an error. Whatever you like to call it, there is a nonlinearity of the physical process of measurement involved, which generates the result. You could absorb it within error specification, or so if you are using a simple thermocouple application over a narrow range, you can say that this thermocouple is linear. Directly from the voltage, you can get the temperature. If you work it on a longer range scale, 500 degree centigrade scale, it will give you a reading for 50 degree centigrade. It will also give you a reading for 600 degree centigrade. Then obviously such a description will not be applicable. If you apply it, you will have errors. So then you may give a table of a thermocouple with some equation saying that it is actually a polynomial. Then you can include the nonlinearity description within the description of the instrument. So what have we seen? So we have seen the structure of the instrument. There is an interfering input, which is additive. There is a modifying input, which is multiplicative. There is a nonlinearity effect, and potentially when this input is varying, then there could be a dynamic effect, which is not applicable for steady input measurements. Then you can ignore it. So this constitutes the overall structure of the instrument. Now we will see that later on. We'll see, today's class is over. Later on we'll see how these factors are actually sort of captured using various performance characteristics of instruments like sensitivity, like offset, like resolution, deadband, time constant, all these things. So that will be next class. So thank you very much. Is there any question at this point of time? Let me stop presenting. So is there any question or anything at all you would like to say?